All right, so as we look into chapter 24, we are looking at data that is paired, data that is related to one another. Paired data. Data are paired when the observations are collected in pairs or the observations in one group are naturally related to observations in another group. The simplest form of pairing is to measure each subject twice, often before and after a treatment is applied. So say I want to test my long jump and the effectiveness of training. I'm going to jump before my training to see my results, and then I'm going to train, and then I'm going to jump and measure my results after the training. And I'm going to compare the two results. Was the training effective? More sophisticated forms of pairing in experiments are a form of blocking, which we'll talk about later. So with this, we are talking about quantitative data, so we want to run a t-test. The paired t-test is a hypothesis test for the mean of pairwise differences of two groups. The key word here is differences. My pen right there. It tests a null hypothesis. So I have one data results. Let's just say this is my test before the training, and this is my data of my jump after the training. And I want to test the differences of the two here. With t-test, we also have confidence interval. A confidence interval for the mean of the piecewise differences, keyword again, between the paired groups. And here's our formula and how we calculate the standard error. Now, since we are running a t-test, we want to check certain conditions. Paired data conditions. The data must be paired. When you have two groups with the same number of observations, it may be tempted to match them up. Don't unless you are prepared to justify your claim. On the other hand, be sure to recognize paired data when you have them. So I'm doing the same thing. I'm jumping a distance. I'm jumping before the test and after the test. Since I'm doing the same result, that is classified as pairing data. We can also make an independence assumption. If the data are paired, then the groups are not independent. So my first jump, it is dependent on my training with the second jump. Randomized condition. The pairs must be random samples. Treatments randomly assigned or assigned to one member of each pair. So make sure something in there, part of your experiments, is randomized. Now, just like with the last t-test, since we're talking about small samples, we don't have to worry about the 10% condition. That's the same here for the paired t-test. And the nearly normal model. If your original measurements are skewed or binomial, the differences, here's that word again, may be nearly normal. So say I were to run my test on how far I jump, and that data looks to be very much skewed. And then I run my test after the jump, and then that data looks very skewed. That's okay as long as when I take the differences of my information, that reflects a normal model. So we want to look at the data differences and not just the specific data points themselves. For example, field workers for a health department compared driving mileage on a 5-day work schedule with mileage on a new 4-day schedule to see if the new schedule changed the amount of driving they did. We'll look at the paired differences in mileages before and after. Is it okay to use data to test whether the new schedule changed the amount of driving? So, the paired data condition. The data are paired because each value is the mileage driven by the same person before and after the change. So, notice how Jeff did both the 5-day and the 4-day. Tom did the 5-day and the 4-day. You don't see any gaps. Let's say like Greg just did the 4-day, or Larry only did the 5-day. That wouldn't be paired data. Paired data looks like this, where they are all together. So I'll need to erase that. This is what paired data looks like. The independence assumption. The driving behavior of any individual worker is independent of the others. So the differences are mutually independent. So Jeff's driving does not affect Betty's driving. And Betty's doesn't affect Larry's. And Larry's doesn't affect Leslie, and so forth. Each driver is independent. These may not be independent, but as long as our visual test subjects are. Randomization condition. The mileages are the sums of many individual trips, each of which experience random events that arose while driving. Repeating the experiment in 2 new years would give randomly different values. So we want to make sure that Jeff isn't doing the exact same mileage as Larry on that. Oh, yeah, and vice versa. We want to make sure all of this gets randomized. When is Jeff going to do his 4-day mileage? When is Tad going to do his 5-day mileage? Make sure those are randomized. Nearly normal condition. Again, we are looking at the keyword differences. So here is my model that represents the differences. And as I see here, it does kind of represent a normal model. So that does verify the nearly normal condition. Since the assumptions and conditions are satisfied, it is okay to use the paired t method for this data. And tomorrow we'll look at